So here we go. We're coming close to the end. This is chapter 2, section 7, piecewise functions. This is the end of, we're getting close to the end of chapter 2, which will be the end of unit 1. And we're going to have a test next week, I said, and I will talk about that more in class. So up to now in this chapter, a function has been represented by a single equation. However, in many real-life problems, functions are represented by a combination of equations, each corresponding to a different part of the domain of the x's. Remember, domain are the input, the independent variable, which we usually use the variable x for. Such functions are called piecewise functions. And a little aside, of course you're all for animal testing. You always get straight A's. Ha, 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 ha. So let's talk about piecewise functions and how these work and what we do with them. So let's look at one first. Evaluating a piecewise function. So evaluate the function for the given value of x. This is my function f. F is built up of two different expressions, x plus 2 and 2x plus 1. Where do I choose which one? Where when x is less than 2, I want to use x plus 1. Where x is greater than or equal to 2, I then want to use 2x plus 1. This is the difference. So as I work through here, I always ask myself, what part of the domain am I looking at? If depending on the part of the domain, I will then choose the part of the function that I'm going to use. So f of negative 5 is less, get rid of some of these markings, negative 5 is less than 2. So I need to do negative 5 plus 2. I use this top because that goes with this particular part of the domain. So negative 3 is my answer. F of 0, again, this is still less than 2, so I still use x plus 2. So this is 0 plus 2, and then this is equal to 2. Here I have f is equal. I have f of 2, so x is greater than or equal to 2. It's equal to 2. So I'm now going to use part of the function that's 2x plus 1. So this is 2 times 2 plus 1. 2 times 2 is 4, plus 1 is 5. And finally, f of 4, again, this is greater than or equal to 2. So I'm going to use 2x plus 1. 2 times 4 plus 1. 2 times 4 is 8, plus 1 is 9. That's the basic idea of a piecewise function. The function is broken up over my domain, and I have different functions for each part of the domain. Let's try another. So here we go. Let's graph this piecewise function. Make sure I didn't go too far. Okay. F of x is equal to 5 if x is less than or equal to negative 3. F of x is equal to x minus 1 if x is greater than or equal to negative 3. Negative 3 is the number that I need to be careful of. That's where my function changes. So the first thing I'm going to do is I'm going to put a dotted line here, because this is where I know my function is going to change. My function is going to be f of x is equal to 5, which we've always said is y is equal to 5, when x is less than negative 3. So to the left of negative 3, I want my function to be 5. So left of negative 3, my function is going to be 5. It's just a horizontal line. At 3 itself, at negative 3 itself, I am not at 5. So I need to put an open circle at negative 3. So I know that I go up to negative 3, but I don't include negative 3 itself. I can't get the circle. There we go. Negative 3 is not up here at 5. Negative 3 is down here where x is greater than or equal to negative 3. Well, then I have x minus 1. Again, so when I'm over here to the right of negative 3, my function is f of x is equal to x minus 1, or as we've always said, y is equal to x minus 1. My y-intercept b is 0, negative 1 is my coordinate. My slope m is 1 over 1 because there's a number right here. So I start at negative 1, and I'm going to go up 1, right 1. That's not right. Let's try this again. I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. And I can do this as much as I want. And I get down to negative 3. Now, I did show that as a closed dot. Is that a closed dot? Well, here you notice that x is greater than or equal to negative 3. So at negative 3 itself, I want a closed dot. So then my graph is going to start at that closed dot, and it's going to go up. This entire picture, that's a little off. This entire picture is f of x. The green line isn't necessarily needed in my final answer. It's okay if you have it. That's to help me see where my graph breaks up. But this is f of x when x is less than negative 3. And this here is f of x okay. This is f of x when x is greater than negative 3. So I break it up over my domain, and these are my two graphs. That's example 2. Let's try another example. So graph the function f of x is equal to 2x minus 1 if x is less than or equal to 1. F of x is 3x plus 1 if x is greater than 1. Again, I want to look at my domain first, and I want to go to where x is 1. This is where my graph is going to be broken up. So I'm going to do blue for less than 1, less than or equal to 1. I want 2x minus 1, so my y-intercept is negative 1. I want to, well, I could rise to and run 1, because that's my slope. Remember, f of x is equal to 2x minus 1. So my slope is 2, which is 2 over 1. My y-intercept is the coordinate 0, negative 1. That's where I got this red point here. My slope is up 2, right 1. Or I can go down 2, left 1, down 2, left 1. That's my line. Since I have equals right here, I want a solid line right there, a solid dot, because that means that is the value when x is 1, and my line is going to go down in this direction. Just like that. What happens when x is greater than 1? Well, when x is greater than 1, again, we have f of x is equal to 3x plus 1. Well, again, my slope here is 3 over 1. My y-intercept b is the coordinate 0, 1. This is what's going to look a little odd. I'm going to start here at 0, 1 to the left of my point 1. I know, but we'll get there in a second. I want to go up 1, 2, 3 to the right 1, up 1, 2, 3 to the right 1. There's my points. Now here's the thing. This point here is not actually part of what I want. I want 3x plus 1 when x is greater than 1. So my graph is actually going to start at this point here when x is 1 and go up. And since it's greater than, not greater than or equal to, I need an open circle right there. That's what my graph looks like. This point is not part of my graph, so I'm going to get rid of it. This black dotted line is not part of my graph. That was just so that I know where things were broken up, so I can get rid of it. This here's left is my graph. So when x is less than or equal to 1, I have this equation. When x is greater than 1, I have this equation. Fairly straightforward. I'm graphing the way I know to graph, but I'm breaking it up over the domain. Let's try something else. So here we go. This is what's called a step function. In a step function, my graphs are horizontal lines, 1, 2, 3, and 4. And they're going to be broken up over my domain in a particular way. So I'm going to start, my lowest number is 0. I have a less than or equal to. So between 0 and 1, I want x to be 1. So when x is 0, x is 0, I want my y to be 1. When x is 1, this is just between these 2 points right here. That's y is 1. Now when I'm between 1 and 2, I want closed at 1 and open at 2. I want to be at 2. So closed at 1, open at 2. My step is at 2. Now between 2 and 3, closed at 2, open at 3, closed at 2, open at 3, I am at when y is 3. Lastly, between 3 and 4, I want to be 4, closed at 3, open at 4. So if you had a little doll, you can kind of walk up this step. And this is why it's called a step function. It looks sort of like a staircase. It's closed on one side and open on the other. It is a function because if I drew vertical lines, this is part of the graph, but this is not. This is part of the graph, but this is not. This is part of the graph, but this is not. So I only hit one point of the graph at a time. That's why the open and closed dots are so important. And that's why the equal to and the not equal to are so important. That's a step function when I'm talking about piecewise functions. Let's look at another. Graph the function again. This is another step function. How much time have we gone? We've gone 12 minutes. Okay. So my x's are from -5 to 1. So -5 to 1. And then from 1 to 2. And then from 2 to 6. Okay. Between -5 and 1, I want my y to be -1. I want it to be closed at -5. And I want it to be open at 1. I'm going to make that blue so it stands out versus the other lines that I put up. Again, the dashed lines are not part of my graph. It's just to break up my graph over my domain. Second part, between 1 and 2, I want to be my y to be 2, closed at 1, open at 2. So my y needs to be 2, closed at 1, open at 2. There's my step. Between 2 and 6, I want to be at 5, closed at 2, and open at 6. There's my step function. Again, it's a function because a vertical line will only hit one point of the graph at a time. This is part of the graph. This point, since it's open, is not. This is part of the graph. This point, since it's open, is not. Again, that's another step function. Write the equation for the piecewise function whose graph is shown. Now I need to do backwards. I need to come up with an f of x that's equal to, I need my brackets. I need functions here, and I need domains here. So I need to break up my graph and see where it looks like. Well, first, the breakup of my graph is at -1 and at 2. It's very important that I also notice that I have arrows on the ends of these and not open or closed dots. So my domains are going to be, this was -1, closed at -1. So I want my x to be less than or equal to -1. This one here is going from -1 to 2. So I have -1 is less than or equal to x is less than or equal to 2. Now that was wrong. Why? Because this circle is open. So this here has to be -1 is less than x. It's closed over here. So then this has to definitely be an equal to. And then I want x's to be greater than 2. It's an open dot, so there's no equal. So those are my domains. What is my function, my ranges? Where my y here is -3. So here I'm going to be at -3. Here I'm going to be where I'm at 2. And here I'm up here at 5. So my step function is -3 when x is less than or equal to -1, which is this line. My function is 2 from -1 to 2, open at -1, closed at 2, and my function is up here at 5 when x is greater than or equal to 2. That is my function from the graph. Graphing a step function, write the equation for the piecewise function whose graph is shown. Let's do another. Okay, so again, I have my function. I'll make this a little bigger, move it a little more to the left. F of x is equal to, again, I have 3 pieces. Where are they broken up? They are broken up at -2, and at 3. So, for my first part of the graph, let's undo that. For my first part of the graph, this part here, my domain is less than -2. So I want x's less than -2. For this part here in the middle, I want between -2 and 3. So -2 is less than x is less than 3. And here I want greater than 3. So x is greater than or equal to 3. Now this has to be equal to because that's a closed dot. This here has to be, right here, has to be open because that's an open, so there's no equal to. These two right here, they're on the same point. If I put equals on both of these, I'm going to have 2 points. I need equal just on one of them. So I'm going to put equal on this one. Could you have put equals on the top one? Yes. Does it matter? No, but I cannot have equals on both of the graphs. So that's my domain broken up. I now need to find my ranges, my functions. What are they? Well, let's see. Well, here's one point. Here's another point. My slope is, if you notice, I have lots of points on this line. And the slope is down one, right one, down one, right one, down one, right one, down one, right one, down one, right one. And so that tells me for this first part, my slope is down one, right one. So my slope is going to be -1. So I start with -1 or -x. If I continue from this point, see down one, right one, down one, right one, down one, right one, down one, right one, I get my y-intercept to be 4. So I'm going to do plus 4. Now, could I have picked 2 points and found my slope and found my y-intercept using point slope or slope intercept? Yes, but rise over run getting me my intersection also works. So this first equation is negative x plus 4. What's the second part of my function? My second part of my function, I'm going to do this one in red. First of all, I have a y-intercept of 10, so I have plus 10. And then my slope here is up to right 1, up to right 1, up to right 1. So my slope then is up to right 1, so my slope has to be 2x. My last part of my function is a horizontal line, and it is at 3. So there is no slope. It's horizontal. Slope is 0. So it's 3. So my function is, my step function is negative x plus 4 when x is less than negative 2. My function is 2x plus 10 when x goes from negative 2 to x less than or equal to. And my function is 3 when x is greater than or equal to 3. There's my step function. Okay. The last thing, I just want you to see this. Another example of a step function is called the greatest integer function. This function is denoted by f of x is equal to double bar x. This is called the greatest integer function. For every real number f, f of x is the greatest integer less than or equal to x. So let's say I pick the number the number 3. Well, the greatest integer function says that 3 has to be 3. 1, 2, 3. It says that 2 has to be 2. It says that 3, 4, 5, 6, 7 has to be 4, 5, 6, 7. And that's true. But it also tells me that the point 1, 2, 3, 4.5 4.5 is between 4 and 5. 1, 2, 3. So between 4 and 5. The greatest integer between 4 and 5 is 4. That's because it has to be less than. The key word is the greatest integer that is less than my equal number. So all the points between 4 and 5 are going to go to 4. All the numbers between 5 and 6 are going to go to 5. All the numbers between 6 and 7 are going to go to 6. So it's always closed on the left and open on the right. This is what's called the greatest integer function. Hey guys, that's all the notes for this night. That's 23, almost 24 minutes. Have a good evening.